Hey guys, welcome to my online classes on YouTube through Science Informatics channel. Today I'm bringing you a new topic on Biot-Savart law. This topic may be as a revision for some of you and might be new discussion class for some of you. Let's start with Biot-Savart law. Biot-Savart law gives a way to find the magnetic field due to elemental current, or say current element. Current element means a small length of conducting wire that carries current. Biot-Savart gives the way to find the magnitude and direction of the magnetic field due to that current element. Consider this figure. This is current carrying wire. Here we have considered a small length DL that also carries the same current as the conducting wire. The magnetic field is calculated or given by Biot-Savart law at some distance from that current element. The elemental flux density at any point due to that current element is given in magnitude and direction by given in magnitude and direction means in vector form. The elemental flux density is given by dV vector is equal to mu naught upon 4 pi I dl cross r cap upon r square, where that r cap is unit vector along the vector r, and mathematically it is given by vector r divided by its magnitude. So if we substitute this formula, we get this expression in new form as dV vector is equal to mu naught by 4 pi I dl cross r vector upon r cube. As I said, r cap is the unit vector along vector r. Mu naught is the permeability of free space. R vector is the radius vector joining the field point and the source point. Field point is the point where we are calculating magnetic field, and the source point is the point due to which magnetic field is produced. The magnitude of this flux density is given by dV is equal to mu naught by 4 pi I dl sin theta upon r square. You can easily get this formula just after using cross product of two vectors. Say a cross b is equal to ab sin theta. Here dl cross r will be equal to dl r sin theta, where theta is angle between dl vector and r vector. And the direction of this magnetic field is perpendicular to both dl vector and r vector, or say perpendicular to the plane containing both dl vector and r vector. Now let's discuss some applications of Biot-Savart law. The first application is the magnetic field at the center of a current carrying circular coil. We can find magnetic field due to different shapes of conductors carrying current using Biot-Savart law. One of these is the magnetic field at the center of the circular coil. Here we consider a circular coil of radius small r carrying current I in anticlockwise direction as shown in figure 1 here. To calculate the magnetic field at the center O, consider a small element of length dl at point A, then join O and A such that O is equal to R. The direction of dl is along the tangent at every point on the circle. So dl will always be perpendicular to r vector, hence we take theta is equal to 90 degree. Now the magnetic field at the center O of the circular coil due to the current element of length dl at point A is given by dv is equal to idl sine theta upon r square, the constant term mu naught by 4 pi. Here theta is equal to 90 degree, so dv is equal to mu naught by 4 pi ideal sine 90 upon r square. If we use the values, corresponding values, now we get dv is equal to mu naught by 4 pi ideal upon r square. This magnetic field given in equation 1 is at the center of the circle due to that elemental length dl only. Total magnetic field at the center is just the sum of such magnetic fields due to such elemental lengths dl throughout the circumference of the circle. So the total magnetic field is obtained by integrating equation 1 throughout the circumference of this circle. So let us see. B is total magnetic field is obtained by integrating that elemental flux density throughout the circumference of the circle. This is integration throughout the closed loop. Here the closed loop is the closed circle. Now we substitute the value of dv from equation 1, and since the constant terms can be made free of integration sign, we are writing this way. Now integration dl means adding dl throughout the circumference of the circle. That gives the circumference itself. So circumference is 2 pi r. Value of integration dl throughout the circumference of the circle is 2 pi r. That is the circumference itself. Now, by simplifying, you get B is equal to mu naught I by 2R. This is the total magnetic field at the center O. If the circular coil has only one turn or a single turn, now if there are n turns of the coil, then we multiply the magnetic field due to single turn by the number of turns to get the expression for magnetic field due to circular coil having large number of turns. Remember this formula? You might use this formula to solve some of the numericals. Okay. Um, since the magnetic field is vector quantity, we must know the direction of magnetic field as well. The direction of magnetic field at the center O is perpendicularly out of the plane of vapor as suggested by the right hand rule. Now let us discuss the second application of Biot-Savart law. Magnetic field at an axial point of a circular coil. Consider a circular coil of radius small a that carries current I in anticlockwise direction when viewed through the right side. The plane of this circular coil is actually perpendicular to the plane of our screen. And the axis of the circular coil is on the plane of the screen. Suppose we have to calculate the magnetic field at point P on the axis of the circular coil. This is the axis of the circular coil at distance x from the center O of the circular coil. For this purpose, consider a current element at point A, and the direction of dl will be same as the direction of current at that point. Now join point A and point P. There forms a right-angled triangle OAP. After joining, you have some geometrical values. Check there. AP is equal to R, OP is equal to X, and OA is equal to small a, the radius of the circle. And angle OPA, angle OPA is phi. And similarly, if we consider another element at diametrically opposite point of A, this angle will also be equal to phi. Now, the magnetic field at point P due to the current element at point A as suggested by Biot-Savart law is given by dV is equal to mu naught by 4 pi ideal sin theta upon r square. Here theta is taken as 90. Remember that dl is perpendicular to r because this r is parallel to the plane of the screen, plane of our screen, and plane of the coil is perpendicular to the plane of our screen. and dl is parallel to the plane of the coil. So dl is always perpendicular to r vector in this case at every point on the circumference wherever you take. So theta is 90 degree. Now after substituting this value, we get the simplified form in equation 1. dv is equal to idl upon r square, and the constant term is mu naught by 4 pi. To get the total magnetic field at point P, we must first of all think about the direction of this elemental flux density. According to Biot-Savart law, we can predict the direction, which is perpendicular to the plane containing both dl vector and r vector. Obviously, the direction of dv vector is at least perpendicular to r vector, here we can say. So dv is directed perpendicular to this r vector, but it is slanted with the axis of the coil. So it has two rectangular components in reference to the axis of the coil. One component dv sin phi along the axis of the coil and dv cos phi perpendicular to the axis of the coil. If we consider the current element at a point diametrically opposite on the circumference of the circle, the magnitude of elemental flux density will be same, and the vertical component of that elemental flux density will have same magnitude but opposite direction. But the horizontal component adds up. So to get the total magnetic field, we integrate only the horizontal component dv sin phi of this elemental flux density. So we do not integrate total dv, only dv sin phi component of equation 1. Remember this. The vertical component dv cos phi cancels out. So we do not need to integrate total elemental flux density. Just integrate the horizontal component of this elemental flux density to get the total magnetic field at point P. Yes, so we integrate only the dv sin phi component. Now substitute the value of dv from the above equation. Yeah, it looks like this equation. Then see here, mu naught by 4 pi constant, current is constant, sin phi is constant, because sin phi is equal to a upon r. A is radius and r vector here in this case is constant because it is symmetric about the axis, so its value do not change throughout the circumference of the circle. And r is just root under a square plus x square by using Pythagoras theorem. So constant terms are taken out of integration sign. Now integrate only dl. Integration dl throughout the circumference means the circumference itself. So we replace that integration dl by value of circumference, that is 2 pi times radius. The radius here is small a, not r. In the previous case we supposed radius r because the radius vector, that is the line joining source point and field point, was the radius itself, so we suppose radius r. Here in this case radius vector is to be supposed or is to be denoted by vector r, so we denote radius by small a, and the circumference is 2 pi a. Now by simplifying you get the result mu naught I a sin phi upon 2r square. Again substituting the value of sin phi a equal to a by r, you get mu naught I a square upon 2r cube. And this expression is also true for a coil of single turn, but in practice coil has large number of turns. So if the coil contains n turns, then the total magnetic field is obtained by multiplying it with number n, as b is equal to mu naught n I square upon 2r. Remember, r is root under a square plus x square. The direction of this magnetic field is towards the right, at point P away from the coil, as suggested by right hand fish rule. Because we have considered the direction of current to be anticlockwise as viewed from point P, the direction of magnetic field is towards the right. Now special cases. First case, if x is equal to 0, x0 means, remember that the field point is at distance x from the center of the circle O. If x is equal to 0, that means the field point lies at the center. So this must represent the previous case. Let's check. As r is equal to root under a square plus x square, r will be equal to, yeah, this is not approximately equal, this is equal to a. So the above formula becomes b is equal to mu naught ni square upon 2a cube. That is mu naught ni by 2a. Exactly the same result obtained in the first case at the center of the circular coil. In that case, we represent the radius by r. Here, radius is represented by a. Okay, let us see next case. If x is very greater than a, then we can neglect a as compared to x, r will be approximately equal to x. So in this case, the magnetic field will be given by mu naught n I square upon 2x cube. Thank you very much for watching this video. I will discuss other two applications of Biot-Savart in next video. Keep on watching. Thank you guys.